immensely hard without them. So without further ado, Mehdi, I don't think that I have anything more to say. The screen is yours. I'm not here to steal the spotlight or anything. So yeah, feel free to share screen and get on with the talk.
Awesome, thank you. I will go ahead and share my screen. Awesome, and that looks like it's working. So thank you so much, Stavros, for the introduction, and thanks everyone for tuning in. I've been really enjoying the conference today. It's been really great. So big thanks to the organizers and everyone watching. It's been a really fun day so far. So my name is Mehdi Vasigh. I'm a senior engineer at Mailchimp, and today I am presenting a talk titled "Build Snappier Apps with React and Web Workers." So yeah, thanks for tuning in. I'm just going to launch right into it. So first, I'll just tell you a little bit about myself. I'm an engineer at Mailchimp, and we build marketing software. I do a lot of work on the front end, but I'm also kind of into a lot of graphics type work as well. I do creative coding, and to be honest, most of the time, if I'm not working, you'll find me kind of nose deep in shader code or doing something with like generative art. So if you're interested in any of that kind of stuff as well, definitely find me online. I have art out there, and just love talking about it, but also super interested and super kind of immersed in the world of building UIs, user interfaces for the web, which is what we're talking about today. So we're going to be talking about specifically using web workers to build better, smoother user interfaces in React. And like I mentioned, I'm online. You can find me on Twitter. So if you have any questions during the course of this presentation, feel free to add them, and I will try to answer if you just ask in the chat. But if not, and if something comes up later, please feel free to reach out to me at any time. Love talking to people. So, so first I want to talk about performance. And this is actually really timely for a couple of reasons. One, because we just had an announcement about React 18 yesterday, which was super exciting. We've also had some talks about performance today. So I wanted to bring up the topic of performance and talk about what it means to have a high-performance web UI. So traditionally, when building web applications, we've concerned ourselves with the initial page load in the past. So for years and years and years, we built websites and web applications that were mostly server-driven and server-rendered. So you would have pages with HTML, like forms, basically communicating with servers, re-rendering the entire page. So this is like still a very common pattern, mind you. Like many websites out there still run like this today. But many of our metrics and much of our understanding about web performance has been formed by this pattern of building websites and web applications. So a lot of the metrics you'll see out there, like time to first byte or first meaningful paint or time to interactive, as well as things like Lighthouse and Web Vital scores, are very deeply tied to this initial page load, this idea of a page load. And this is definitely very relevant in a lot of different cases. So anytime you have a website or web application that's navigating between pages, downloading new documents or JavaScript bundles and kind of serving them to the user, anytime you have any kind of server rendering and the hydration that happens in the client, these are important metrics to watch because these are code paths that are getting hit very frequently. Something that we don't talk about as much in the web, because kind of it's a new thing, right, is afterload performance. So this is essentially like smoothness, responsiveness, and things like memory efficiency. Now, these ideas and these concepts are a lot more, I guess, like well fleshed out in other disciplines of engineering, such as like game development or interactive media and that type of thing. But they're relatively new to the web, mostly because highly interactive web applications are relatively new to the web. It's something that we're really just now starting to dip our toes into and build these really interactive, really rich experiences on the web that compete with native applications and what we're traditionally used to as like really kind of rich interactive applications. We're no longer building websites, we're building web applications. As an example, this isn't like a totally, I guess, like maybe it's not the first thing you think of when you think of like a rich and interactive application, but one application where afterload performance might be very important is something like Google Calendar, where you might have a Google Calendar tab open for the duration of your workday or the duration of your work week or even months and not close it. So time to first byte doesn't really matter so much as smoothness, memory efficiency, other memory leaks that are just making it slower over time. Is the application responsive to interaction, or is it driving you mad, right? Every time you use it, there's an additional event listener and there's a memory leak, and it just gets slower and slower. So today, mostly we're focusing on smoothness. And what smoothness means, what we mean when we talk about smoothness, is maintaining a stable frame rate. So if you're a gamer like I am, you care a lot about frame rate. So like you benchmark everything against like how many frames am I getting? Am I getting a consistent 60 frames per second or like 30 frames per second, whatever? Or am I getting more? Like how many more frames am I going to get if I have like some beefier hardware? But essentially, anytime you have motion involved, it's really important to have a stable frame rate and a frame rate that produces motion in a smooth way to the point where it doesn't introduce visual jank to the user. So stability is kind of a complicated topic with frame rates, but we can kind of boil it down to some somewhat simple math. So if we consider that we want to target 60 frames per second, and there's an asterisk there, I'll explain what that means, then the math essentially turns out to be that we have 1,000 milliseconds or 1 second, 1,000 milliseconds in a second, and we want to render 60 frames in that second. So we have about 16 milliseconds to produce a frame, essentially. Run all the code that is required for the browser or whatever host environment we have to render a frame. Now, if we are rendering every single one of these frames, we can actually just kind of shave off like 4 to 6 milliseconds of those frames, because depending on what happens, the browser itself has to do some work internally inside of like the browser engine to produce that output as well. So it's not just our JavaScript code that's running and producing frames. Obviously, there's like CSS, there's document stuff with your HTML, the document changes, the CSS changes, things that have to get painted. So, and of course, the JavaScript engine has to run, right? So we can say that that overhead is going to account for about 4 to 6 milliseconds per frame. So that means that if we're really trying to paint 60 frames per second and we're running JavaScript on every frame, we have about 10 to 12 milliseconds to run all of our JavaScript code to produce a frame without dropping frames, without essentially like eating into the next frame's budget. And that's an important concept, is the frame budget. It's something to be aware of as a guiding light or a North Star, and say like, this is how I'm going to evaluate my code. Am I using up all my frame budget? Do I have any frame budget left? Or if I'm using or exceeding it, like how can I cut that down? Now, I do have an asterisk here, and that's because the 60 frames per second metric that I'm using here is a little bit of a generalization. In reality, the browser is not actually painting 60 frames every second. So the browser is smart enough to know if things have changed or not changed. And if nothing has changed on the page, there's no reason to kind of run a bunch of code and paint the same frame over and over again. So like if you look at the frame rate of your applications, when nothing is happening, it should ideally drop down to like near 0, right? And then when there's a lot of motion on the screen, it should approach 60. But generally, it's a good mental model to have to consider the most interactive or like most motion in your application as 60 frames per second and work backwards. So I mentioned earlier, eating into the frame budget introduces visual jank. So like what actually happens when we exceed the frame budget? Well, we can, in order to like kind of think about that, we need to just have a little bit of a mental model in place of the browser pixel pipeline or the rendering pipeline in the browser. So every time really anything changes, or every time you produce a document or a web page in the browser, there are several steps that the browser goes through in rendering the page to the screen. They can broadly be broken down into these sections that you see here. So we have the JavaScript execution phase or stage, and then the two in purple are style and layout. So these are kind of like CSS related and like document layout related tasks that the browser is doing. And then there's an additional 2 stages called paint and composite. The reason these are color coded in this way is because depending on the properties that you change in your CSS or your HTML, some of these steps can be skipped. So if you've ever heard the kind of best practice of you should always use CSS Transforms instead of using like height and width and stuff to animate your elements, it's because doing so avoids having to avoids a reflow of the layout, which means you can skip that step and the browser has to do less work to produce the next frame. And so, like, if you imagine if you're doing a transition, that is a highly that's a high movement thing that you're doing, right? There's a transition there, there's animation, so you want to be as efficient as possible. Now, you might notice here, I'll actually go back, JavaScript is a small part of this. So I think as oftentimes in the modern world, as app builders and app developers building with JavaScript, we tend to think that JavaScript is everything. And everything in JavaScript, like CSS in JavaScript, markup in JavaScript. And that's a really good pattern for componentizing our code, and component frameworks really benefit from this. But in reality, there's a lot of other stuff going on as well, right? So if we kind of try to cram everything into JavaScript, we start running into problems. So in this example, I'm trying to basically illustrate and say that everything that you do in your React application has to fit in the yellow box. So your CSS and everything else, obviously, like your document stuff, is outside of the JavaScript box. But anytime you're running JavaScript, it has to fit into this yellow box. So that includes your actual UI and local logic. So like your React application and state management. It includes, if you're using something like styled components that has a runtime engine. So your CSS and JS runtime is also going to fit into that box. The front end framework itself, so like React and React's virtual DOM are fitting into that box, and that's JavaScript code you're running constantly. If you're using something like Redux, or you are using some kind of complicated state management library that could eat into that portion of the frame budget, and pretty soon, depending on the amount of code that you're kind of running, you might exceed your frame budget and go past this red line. Now, I don't mean to imply that just by plainly having some UI, some CSS and JS, some front-end framework, and state management, you're going to exceed your frame budget. But the point I'm trying to make is the more that you add, the more layers that you add inside of your JavaScript, the more likely it is that you might do so. And another way of phrasing it is the less room you have for your code, if that makes sense. So what happens when we exceed our frame budget is that these boxes can extend way past 16 milliseconds and push the remaining frames kind of further out. And that means that JavaScript, I'm sorry, not JavaScript, but like the browser has to wait until this entire flow from JavaScript style, layout, paint, and composite, that's going to be longer than 60 milliseconds, has to wait for all of that to finish in order to be able to render the next frame. Now I have an example here, and I'm going to show you. So this is obviously clearly like an animation here. This is a canvas-based animation, and this is actually rendering in like a request animation frame loop. And so it's doing it like 60 frames per second, essentially. And the form here, what it's doing is a recursive Fibonacci number calculator. So this is like the most inefficient code ever. It's not memoized or anything like that. It's only there to kind of prove a point. But so like if we do some low amount of work, so if I try to calculate the number at position 4, you can see our computation takes about 0.17 milliseconds and we get a result. No problem, animation's still running. I happen to know there is a number that makes my browser crash, and I'm not going to reach it, but I'm going to approach it. And the closest I can get is 42. So hopefully this doesn't break anything, but I'm going to try to calculate this. And you'll see for about 5 seconds, this just completely blocked our animation, right? We have some additional JavaScript that's running, and because that code is running, our animation can't run until all of that work is done. Now, what we want to do ideally is to do this in a non-blocking manner. Like, let's imagine, for example, that you just absolutely have to calculate this number and there's no way to optimize it further, or maybe it's just too complex to optimize it further. You can do it in a non-blocking manner in a worker, and we'll explain all that as we move forward, but I'm just going to illustrate. So you can see our animation continues to run, It's taking just about the same amount of time to calculate, but the difference is that our animation is not blocked, right? Like you're doing the work in a separate place that we're going to talk about that doesn't block your animation code. So you might be asking, if you've seen the announcement yesterday about React 18, isn't this what React 18 and Concurrent React does? If you're familiar with Concurrent Mode in React, it's not really a mode anymore, but it's a concept that the React team has been working on for a long time, where expensive code can be interrupted to ensure that the UI can paint, right? So if you're typing into an autocomplete box and that's doing a lot of computation in the background, we want to make sure that your keystrokes still register, like you still see your text pop up in the input, and not have that kind of filtering logic block your code. And the answer is not quite. The reason for that is, well, in order to explain it, you kind of have to get into the difference between concurrency and parallelism. So everything actually that we do in JavaScript land is concurrent. JavaScript thrives in this kind of concurrent environment because the JavaScript engine relies on an event loop. And what concurrency means is that a single CPU core or a single thread can do multiple things seemingly at the same time, but in reality, it's just doing bits of each thing one at a time. So in other words, to have work that is concurrent means that you should be able to interrupt the work, do something else, and then come back to it and pick up where you left off. These two are not mutually exclusive, obviously, but when we talk about like concurrent React in React 18, at the end of the day, those two tasks, so like typing into the input and filtering the data to show the autocomplete results, those two are still going to run on the same thread. And regardless of how much you interrupt the expensive work to prioritize the critical work, at the end of the day, they're still occupying the same, they're consuming the same CPU resource. Now, parallelism is a little bit of a different concept. And this truly means doing two things simultaneously in two different places. So doing two different tasks on two different CPU cores. And clearly, like in this example, like it's happening faster, the two are finishing. That's not necessarily the case every time. And that's not really the focus here. It's not about speed. It's more about unblocking task one while task two is executing. There's no part of task two that's going to interfere with the execution of task one. So I mentioned this, I kind of touched on this earlier. We talk a lot about how JavaScript is single-threaded. And there's one single execution context where all the code runs. And if a function takes too long to execute, the thread is blocked. And when we talk about blocking, we frequently kind of refer to it, or like the classic example of blocking code is like a while true loop. So if you just do while true and you don't have an exit condition, your extremely important function will never run. This code is never reached because the thread is completely blocked. But what if I told you there was a way to have JavaScript that is multi-threaded? And that's not just something I'm fantasizing about. This is a real thing. It's been around for a very long time. It's not a new API to the browser. And it's not traditional multi-threading in the way you might be used to if you're working with systems level languages. But the browser does offer an API called the Web Workers API. And it allows us to do work in parallel using separate threads or separate execution contexts entirely. So you can have essentially two different threads talking to one another, but relatively isolated and doing different work at the same time in a truly parallel way. Now, I do want to touch on this. This is a common misconception about web workers. Web workers are not the same as service workers. They're pretty different concepts. They have similar names, which is kind of unfortunate because they're also like shared workers, and it's very easy to kind of confuse them. But service workers, if you've used service workers in the past as like a proxy or kind of like offline solution, they solve a different problem, even though they do share some characteristics. So the naming kind of makes sense. But web workers are a different concept entirely. So let's come back to this. And I want to actually demonstrate something with this example. So here I have my Chrome DevTools open, and I've navigated to the Performance tab. And this is a really great place, actually, if you ever want to evaluate kind of qualitatively, honestly, because there's not really good metrics for frame rate stability, but to analyze and just kind of look at the performance of your application. The Performance tab is a great place to do it. But I'm going to illustrate what actually happened when I ran the blocking code. So I'm going to hit record. I'm going to hit 42 and hit enter. And I'm going to stop since this is complete. So a whole lot of stuff, obviously. The animation itself, this example is running in an iframe. So I'm going to focus on this iframe. And you can see here, if you zoom in on this flame chart, these vertical lines that you see, if I actually zoom in really close, are my animation frames. So you see this task, I have an animation frame that's fired. So this is all the JavaScript required to actually produce the animation, which is just moving a ball, basically. The purple part, which is the paint and composite parts of, the paint and layout parts of the pixel pipeline that I talked about. And then the composite step, which is in green. And this happens obviously very frequently. So this is constantly happening. This is happening about every 16 milliseconds. Now I'm going to skip forward to this right here. And this is when I actually hit calculate. So this giant call tree is every single call of that recursive Fibonacci function that I was talking about. But because it's running in the same thread as my animation, it causes a 5.2 second long task that pushes all of the frames of animation out and causes dropped frames, because the browser essentially has to say, I can't paint this right now. I have to do all this expensive work. So I'm going to clear this and show you the non-blocking example really quick. Hit record to calculate. And it's done. So I'll hit stop. And now this time, what happened there? I'll try it again. Perfect. So this time you can see we have a frame. So this is the actual main thread of this iframe here, as well as the worker. And they're two separate contexts. So the entire time the animation's running, there's no code running, there's nothing executing in the worker. And then when it actually runs the Fibonacci calculator, we still have the same amount of work being done. So the CPU is still having to compute this. However, we are able to continue our animation frame. So we're still maintaining that frame rate. We're still doing everything. So again, this is hopefully what you expected, given what we talked about. But I did want to illustrate this DevTools view, because it's not one that we use very frequently in web dev. Generally, it's not like the bread and butter, but it's a really, really good place to quickly visualize how certain functions are blocking render, and also really good way to kind of visualize the worker and what it's doing. So hopefully that was helpful. I'm going to continue now. So let's talk more about web workers in detail and what they are. So now that you know kind of what they do and the problem they solve, web workers are essentially a separate JavaScript execution context, like I mentioned, and they communicate with the main thread via messages. So there is no shared memory between the main thread or other workers. Now, there's a little bit of an asterisk here as well, because there is a JavaScript type that's been introduced recently called shared array buffer. So this is specifically for multi-threading on shared memory. But that's not something you would see in 99.9% of the time just building web applications. Everywhere else, memory is isolated between the execution context of the main thread and that of the worker. And the way that you communicate between the main thread and the worker is using the post message API. If you've used iframes or anything else offering post message, you might be familiar with this. But essentially, the main thread can post a message to the worker using worker.postMessage. This triggers a message event that you can listen for in the worker using add-event-listener, do something with it, and then post a message back using self-post-message. And the main thread can listen for the message event and kind of handle it on that end as well. Now, important to mention, every time you do this, the data is actually copied between the two. So usually it's not an expensive operation to the point where it would block you from, or it would be like slower than the work that the worker itself is using or doing. But it is something to be aware of. And because of that, you can't just, there are a limited subset of types and JavaScript objects that you can post message back and forth between the two threads. So for example, you can't pass a reference to a function, but you can pass a blob. You can do any of the primitive types like string, symbol. There are other more complex types like the regex object that you can pass as well, but you can't pass the state of an instance. So that's something to be aware of as well. Now, like I mentioned earlier, the web worker API has been around for a very long time, so browser support is actually pretty excellent, going all the way back to IE 10 and classic Edge 12. So you can see here the global percentage is something like 98.18%, and the only exceptions are some of the more niche browsers like Opera Mini. So depending on your needs, you should be in pretty good shape to use web workers pretty much everywhere. So now I'm sure like you've seen plenty of diagrams. It's been great. It's been very conceptual and talking about CPU cores. And you probably want to look at some code and see like, hey, what does this actually look like in action? So here we have, this is like the most bare bones example of a web worker that you can have. And I'll kind of walk through it actually. So at the top here, we have I commented it as worker.js, but think about this as just a separate file. In this file, you have a function called handle message, which is handling message events. And inside of handle message, the event that we receive, all of the data that's been passed via post message is going to be stored inside of the data property of the event object. So, if you have an object here, like if you want to create some kind of your own data structure, like a message with a type and a payload, similar to like Redux actions or something like that, you can do that. And you can handle your message inside of your worker and decide what to do with it based on the shape of it. In this case, what we're doing is just post messaging a simple message with the string ping. And inside of our handle message event listener, we're checking for ping. And if the data that we receive is ping, we just post message back on line 5 the string pong back to the main thread. Now, in the main thread, in the main.js file, we're constructing a worker instance on line 14 by using the worker constructor, and we're passing into it a path to a file. Notice I'm using the word file. These are they do actually have to be separate JavaScript files entirely, so like separate JavaScript bundles. And very similar to the code inside of the worker, we're adding an event listener for the message event and just logging it. And so on line 20, when we post message the string ping, eventually, and when I say eventually, on the order of like a millisecond or two or something like that, we'll see the message pong log to the console because our event listener on line 17 is doing that with the event data that we get back. So everything else that you're going to build with web workers is for the most part going to use this pattern. I say for the most part because there are additional APIs available to web workers as well. We'll talk about that. But this is kind of like your bread and butter. Now, I touched on the separate files in the previous slide, and it is like you do need separate JavaScript files that are going to be initialized as a worker and your main bundle. But bundlers make this a lot easier. So you might think like in your worker, you might need node modules, like NPM modules that you're installing, or to run them through some kind of pre-processing using like transpiler or something like that, or you're using TypeScript. So many bundlers have support for web workers. It depends on the bundler how they're supported. So there's no unfortunately, there's no uniform standard syntax and standard kind of level of support that you'll see across bundlers. But I have a couple of examples here of ones that are exceptionally good, in my opinion. So Vite, which if you haven't used Vite, I would highly suggest you check it out. It's a new kind of development tool and relies on rollup for bundling. But Vite handles web workers by allowing you to append this question mark worker, I guess, like identifier at the end of your import path. And when you do that, it treats your import as a worker constructor. So you can just say worker equals new ping worker and just use it as is. And Vite is smart enough to kind of treat that as its own module with its own dependency tree and kind of emit two separate JavaScript files that are just referenced the way you would expect or you would hope. Parcel does something similar. However, with Parcel, you actually have to pass like a relative path to your worker module. So if you literally in your source code have like a ping.worker.js adjacent to your JavaScript module that you're importing in, you can pass that path into the worker constructor and create a worker instance that way. But very similar to the Vite example, this kind of works as you expect. Now, if you use something like Rollup or Webpack, there are plugins available for other bundlers as well. Even if you use like more like framework type setups for your application, like Next.js, there is guaranteed like a way to handle web workers for your setup and for your stack. You just might have to do a little bit of digging. As an example, at a previous job that I had, we had a create React app application. And so the way we enabled workers, web workers for our application was to use like React app rewire to extend the Webpack configuration and use worker loader, which is a Webpack loader. So you might have to get your hands dirty a little bit. If you're using some of the newer tools, it's handled a little bit better. But you know, like I said, it's an older API, so support is pretty good. The really neat thing about workers that plays really nicely with some of the newer libraries that are out there are that you can essentially, just like any other asynchronous code, you can treat workers like just an asynchronous function inside of your code, right? So in this example, I am actually using React Query. If you've not used React Query, it's a really neat library that allows you to kind of manage asynchronous resources inside of your React code using hooks and not have to worry about async state. So here I am defining, you know, I'm importing my worker and then defining a render markdown to HTML function. Now this example is like a very simplistic markdown renderer and previewer. In this function, I'm returning a new promise that is internally basically like taking the markdown that's provided to the function, post messaging it to a worker that is not pictured here, but has like a markdown to HTML renderer inside of it. That's like an expensive operation that you might want to do as the user is typing, but not necessarily on the same thread or consuming the same resources as the UI. So it'll post message and then listen for the message event, get the HTML data that's sent back, and then resolve the promise. So to the consuming code, you're not thinking about workers and post message. You're just saying, I have a function that returns a promise that resolves system HTML. And you can take advantage of that using tools that are built around promises. So React Query expects a function that returns a promise as a resource, and it just uses the state of that promise to manage the what's returned from the hook. So you can take advantage of that by passing your render markdown to HTML function into React Query. And just as your markdown prop on line 19 changes, so does your, so your render markdown to HTML function gets rerun, and your data returned by React Query is updated, and your UI updates accordingly. There's also some other neat libraries. One that I really enjoy using is called Comlink. And Comlink, what it does is make you feel like you're not using a separate thread. And it does that by essentially making your web worker code feel like a local object. What I mean by that is, you can see in this example, I'm defining in a worker.js module a class, and this class has a single method called ping, and all it does is return pong. But instead of exporting, like typically I would do like export default my class or something like that and just import this module somewhere else, I'm exposing it using Comlink, right? And Comlink is handling the process of setting up all of the boilerplate code required to make this worker behave the way we expect. On the other side, in the main module, wherever we're consuming this class, we're importing Comlink again and importing the worker and using the comlink.wrap method to wrap the worker constructor. What this returns is a local instance, which is essentially a proxy to the off-thread instance of our object. So we can create this instance using new myClass, but the quirk is that this returns a promise. And on line 21, we can essentially just await the invocation of instance.ping or any other method that we define. Now, everything here is going to be asynchronous, so you have to use like async await or like everything returns a promise basically. So you have to treat it as async code. However, you don't have to think about post message, and that's kind of like the main point of Comlink. It makes your code feel a little bit more natural. So those were some examples of just kind of like how you would use web workers in code. You can probably come up with 100 different ways. So if you do come up with a cool usage of web workers, please let me know. I always love seeing web workers used more and more in not just for like super compute heavy applications, but also just where it's more practical or provides a better user experience. But I've also got some ideas in terms of like where it makes sense to use web workers. So let's go through them. The first is obviously like CPU intensive work. So anything that would block the UI, or if you identify a path of code inside of your application that's particularly CPU intensive and always feels janky, that might be a candidate for code to move into a worker. If you're working client side with a lot of data, so I mentioned an autocomplete. So if you're doing a lot of filtering, if you're doing text search, if you're doing anything that's just, you're massaging a lot of data and you feel that the experience that you're trying to provide is intended to be very smooth, and it just makes more sense to have that data live off of the main thread, which is mostly concerned with your UI. It might be a good place to use a web worker. Obviously, like traditional, one of the more like kind of common compute intensive tasks that you might do is like image processing. So image processing is a great candidate. If you want to do anything in parallel, you can spawn as many workers as you'd like, and the browser will just they're essentially, if you're familiar with multi-threading, they're essentially green threads. So your browser is going to manage what CPU core is like. It's going to manage the hardware to software kind of connection, but you can spawn workers from workers. You can spawn as many workers as you'd like. So you can, if you have 10 tasks that need to be done, you can spawn 10 workers, have them all report back when they're done, and then aggregate the results in a single worker and report them back. If you obviously, like if you identify that frames are being dropped in some of your animations, or if you're building an app with a lot of animations, like an editor or something that's very interactive, or a game, you might just want to start with putting as much code as you possibly can inside of workers, just because it would free your main thread up for UI responsibilities. And also, just like I mentioned, anywhere else that you have isolated hot path code that you think would live inside of a worker comfortably and not be subject to its constraints, which is the next slide. So when not to use web workers. So if your work is IO bound, so if your constraint or your limitation for performance is the network and not necessarily like CPU usage, you're not going to get any benefit from doing that work elsewhere. The browser's concurrency model is plenty good enough to handle juggling like a network request that's in flight and your UI work. So in that case, it does make sense if you are doing something with that data when you retrieve it to kind of do it inside of a worker. The fetch API is available inside of workers, but not necessarily for just doing any IO work. And the second part is DOM manipulation. So because the worker context, like I mentioned, is a separate context entirely from your main thread, there is no concept of a document. There's a different global object available. You'll have much of the same APIs available to you, but there is no document. There are no DOM manipulation methods available to you. So the DOM API is off limits. So obviously, like anytime you have anything you're doing with the DOM, it has to be on the main thread. Another example is local storage. So there's no local storage inside of your web worker. There is IndexedDB. So a common pattern I've used in the past is to use IndexedDB to store and cache data on the main thread. and then retrieve it in a worker thread and manipulate it in some way and report back to the main thread. However, if you're, just plain old local storage, unfortunately, is not available for use, and then that's because it's synchronous. And also, like I would say, prematurely is another example of when not to use web workers. If you're working with on a personal project, by all means, go for it. I would say if you're on a bigger team and you would think that the complexity added by using web workers and the additional code that you would have to write and explain to your colleagues isn't necessarily worth the performance gain that you would get, then I would say probably it's not a good use of web workers. And that would be something you would have to just kind of evaluate on a case-by-case basis, identify like what you're trying to do, what your goals are, and then make that decision with your team. So I think that's about it for my content. So thank you very much again to the organizers, to Stavros, and everyone who's been watching. I think we have, do we have any questions? Doesn't look like we do in the chat. Yeah,
it doesn't look like it.
Yeah,
I found it actually extremely helpful. Yeah, well, they may always get the questions like after a couple of days. You never know, right? With YouTube. But Mehdi, that was extremely nice. I really like the concept myself. So it's props to you, of course. Right. Thank you so much for the talk. Actually, it's been immensely helpful. And for all the guys watching, of course, we'll be sticking back in about 15 minutes. The next talk. Again, I want to thank all the speakers and, of course, Mehdi for being here and taking the time to get this awesome presentation up. It was a pleasure to talk to you. And with the rest of you guys, we'll sync back in about 15 minutes. So see you then.